This is section 10.2 on regression. This section introduces a method used for finding the equation of a straight line that best fits the points in a scatter plot of paired sample data. The best fitting straight line is called the regression line, and it is an equation called the regression equation. We can use the regression equation to make predictions for the value of one of the variables given some specific value of the other variable. Regression line, or the line of best fit, or a least squares line, is a straight line that best fits the scatter plot of the data. Our regression equation is going to be y hat is equal to b naught plus b1 times x. Algebraically describes the regression line. The regression equation represents a relationship between x, called your explanatory variable or predictor variable or independent variable, and y hat, which is called your response variable or dependent variable. So the explanatory variable is used to predict the response variable. So example or box here before we get into that. It says find the equation of the regression line with the TI-8384 calculator. So if you notice, we're still using F, which is our LinReg t-test. You're still going to be putting your data into L1 and L2. And then we have a list of requirements up here. It says the sample must be a simple random sample. We have to have quantitative data. Scatterplot shows approximately linear, and the data contains no outliers. It says remove any outliers if we have any. So the example says, using the bill and tip data, find the best predicted tip amount for the dinner bill of $100. So we have a bill and a tip amount here. So pause the video and put in your values into L1 and L2. L1 is your X values, L2 is your Y values. And then we need to go to LinReg t-test. And when we do that, I'm going to go back up to page 1. And you will notice that on this, when you put in your input, your output, you're going to get a few values. You're going to get a linear regression line right here. And you're going to have an A and a B value down here. So it's y equals A plus BX, and you need to substitute those values in to form your equation. So going back down to our example, on bill and tip amounts, we have our equation is going to be y, and we're going to put a y hat because it's our estimator from this data that we have, equals, and it's A. And if you round A, let's round it 3 decimal places. We have 0.347 plus B, rounding 4 decimal places, is 0.149. And then we have an X. And you can rearrange those variables. So I'm going to put down or. You can have y hat is equal to 0.149x minus 0.347. That looks a little bit more like you would have seen it in Algebra 1 class. And so what is the rate that we are tipping? That is like your slope, that percent that we would have here, the value that's with the x. And so it's 14.9% tip rate. And we get a little bit more into that later on. On the next page, there's another example that we will work out together. So I'm going to go ahead and circle that, and we'll look at that in our little mini lectures. And then we talk about residual. So residual is the error value between the predicted value and the observed value. So residual is observed y value minus predicted y value, and the criteria for determining the line that best describes the relationship between the two variables is based on residuals. And it's the most popular technique for making the residuals as small as possible. It's called the method of least squares. And if you notice, there's a line on these two examples, and the points on the first line here are really far away from the actual line the points are, whereas the second equation, the second line, is really close to those points. And so that has smaller residual, which means that our line is a better predictor. So analyzing residuals to determine whether a linear model is appropriate to describe the relationship between the variables. We have a residual plot. You will not be required to do this on your own. This is a scatter plot with residuals on the vertical and the explanatory variable on the horizontal. If a residual plot shows a pattern, such as a curve, then a linear model is not appropriate. If a residual plot shows no pattern, then a linear model is appropriate. So this is not something you're going to have to graph on your own. However, you could be given a graph and asked to kind of interpret it. So determine the variance of the residual constant is constant. We have a constant error variance. Homoscedasticity on a residual plot is the spread of the residuals. It's increasing or decreasing as the exploratory variable increases. We need to check for outliers. So if you notice in the first graph, there is no pattern that is going on. So since it shows no pattern, a linear model is okay. So for this one, we would have a linear model is okay. So linear. And the other two that we have, there is a pattern. And so that would not be okay. That middle one is when we have some kind of issue with it being constant. But again, no pattern would mean that it would be linear.